Well, I'm told I have a very large Texas accent, so I hope you all can understand me, okay? This year's program is open clusters and asterisms, and so far we've only had one decent night for observing, but that one night we handed out 20 pins. People observing through the clouds, and I think that's quite remarkable. The smallest aperture telescope was a 6-inch telescope by the Copernic Observatory in New York. And the idea for this year was to get people to look at objects they may not have ever heard of before, that somewhat sounds obscure, but yet they're bright and could be seen in small aperture telescopes. So hopefully tonight we'll have decent skies. I don't know if it's going to clear up or not. I think the forecast says no, but we'll see. But first, I want to acknowledge the pen that we're handing out. Eileen Myers did a wonderful job. This is the most beautiful pen, I think, that we've had so far. I'm not doing this program by myself. I have Eileen to work with. She is a pure joy to work with. She does the pens, and in every organization there is a few people that make that organization work, and Eileen is one of those people. So for the 2 or 3 people here that don't know you, would you stand up and let's give her a big applause. This lady does a lot of work for Stellafane. It's amazing. She's amazing. But anyway, this another thing we want to announce. Since we're having bad weather, people that have observed 10 pins or 10 objects, 8 objects, we don't care. We'll give you an observing pin. And Eileen's got plenty of them over here if you have done that. So we want to try to make it easy for people. All right, a few things I need to explain. This is somewhat of a technical nature, so I'm going to try to make it as untechnical as possible. But I need to explain a few things. Radial velocity and proper motion. Radial velocity is line of sight velocity, whether something is going away or coming towards us. And we use that as a distance modulus to determine how far away objects are, based on spectrographic measurements of wavelengths of light. If the light is stretched, it's redshifted, that object is moving away from us. If it's blue shifted, it's coming towards the Earth. And the amount of redshift or blue shift in the wavelengths is a rough indication of how far away that object is. The proper motion is the proper motion of the apparent motion of the stars in the sky. And when we do the calculation, it reveals the real movements of the stars. The Milky Way is rotating, the stars are rotating around it, the Earth's sun is rotating around it, but each star has its own individual motion. And when we measure the proper motion, we can determine how individual stars are moving, and that tells us whether objects are gravitationally bound or not in an open cluster. Astrometry covers all of this, and it's the oldest branch of astronomy. And typically when stars move, they move in fractions of a arc second. Typically they're measured in milli-arc seconds per year, or 1,000th of an arc second, which is extremely fine, but that's how a star's apparent movement from our position in the universe. Okay, Gaia Space Observatory stands for Global Astrometric Interferometry for Astrophysics. It was launched in 2013 by the European Space Agency, and a lot of people are not aware of the tremendous science that Gaia is turning out, because it doesn't do pretty pictures like the Hubble Space Telescope or the James Webb Telescope. But this in and of itself is every bit as important as those imaging telescopes. In fact, it's awesome. There's no area in astronomy where Gaia has not impacted. There's been 3 issues of data. 2016, 2020, and 2022 is the latest. And basically, it measures radial velocity and proper motion, which I just talked about. But it gives luminosity, it gives temperature, it gives composition of stellar objects, and it's rewriting astronomy books as we know it right now. It is sensitive enough that it can measure the diameter of a pinhead on the surface of the moon. There's never been a means of measuring radial velocity and proper motion to that degree of accuracy before Gaia. And basically, it's going to, in its 10-year estimated time frame, it's going to measure about 2 billion stellar objects, which is about 1% of the galaxy. But nevertheless, that is a lot of data. And it's going to target each star 140 times over the 10-year period. And it takes a measurement of where that star is, and then it does it again, and it does it again, and it does it again. So any movement of that star will be recorded with a high degree of accuracy. There are 2 mirrors on board that are 1.45 meters apiece, and it rotates, and that rotation is where they get the data, get the results from. It measures 50 million stars a day, 500 million data points a day, and 100 high-resolution spectra per second. So that's an incredible amount of information. And the latest issue was June of 2022. And each issue improves upon the previous issue. So this is an incredible amount of data gathering, and you'll see quite a bit of this later on in the talk. The key to proper motion is first you have to know how far away the object is, how distant that star is from the Earth. And I mentioned spectroscopic analysis of the wavelengths of light. Another method is trigonometric parallax, which basically uses the one astronomical unit, which is the distance from the Earth to the Sun. And if you take a measurement in July or January and another one in July, you have a baseline of 186 million miles. And you then look at a background object and see how much that object gets shifted. And that's called parallax. And you can do that if you hold your hand up and you open one eye, or if you blink one eye and then the other eye, you'll see objects in the background move. And if you move it away, that movement gets smaller and smaller and smaller. Someone figured that how far out do we need to go to get a shift in background stars of 1 arc second? And that works out to 3.26 light years, and we call that a parsec. And parsec is short for parallax second. So that's where that comes from. But this is a highly accurate means of measuring stars that are fairly close to the Earth, and this is how Gaia also measures the distance to stars with a high degree of accuracy. Another way is the inverse square law. If you take intensity and 1 over the distance squared, you can come up also with a distance to objects. When the distance of an object emitting light is double, the intensity of light received from that object decreases by a factor of 4. If you go the other way, if you get a 10-inch telescope and you go to a 20-inch telescope, you're increasing your light gathering ability by 4, not twice, but by 4. But we can use this to determine how far away objects are, because different stars have different classifications depending on the mass, depending on the size of that star. And a B-type star, for instance, has an absolute magnitude of -6 to plus 0.29. Absolute magnitude is what a star looks like at a distance of 10 parsecs, or 32.6 light years out. So if we know that is the brightness of that star, And when we look at another star, we can compare it against this, and we can, using the inverse square law, and we can determine how far away that object is. So there's 3 ways of determining radial velocity. And as I said, radial velocity is the key to getting proper motion. It's also confusing sometimes because astronomers don't always use the same method. So they come up with different distance factors about how far away something is. So it can be confusing sometimes. The Milky Way galaxy, when we look at it, this is what we call the galactic plane. This is where the star clusters are located, along the plane of the Milky Way. When you look up in the night sky and you see the Milky Way, that's the plane of the Milky Way galaxy. It has a scale height of only 180 light years. The open clusters form in this area here, this dusty gaseous area in here, and young clusters are located close to the galactic plane, and over time, a lot of times they will venture away from it. So the older clusters a lot of times are greater distances from the galactic plane than what we see normally along the plane itself. Observation perspective, this is kind of interesting. The sun actually oscillates around the Milky Way in a sinusoidal fashion. It takes the sun about 220 million years to make one revolution around the sun. It's made about 45 of them in its lifetime, as long as the sun has been in existence. Its amplitude, it is 326 light years, and right now it's 55 light years above the plane, which for us is fortuitous because we're not encumbered with all of the Milky Way plane. We can look down on things. Our night sky is relatively unencumbered of objects that we have to look through in order to see other detail in other galaxies. We're currently moving upwards at 4.5 miles a second, and we'll next cross the plane of the galaxy in about 30 million years. Another thing is the orientation, the axial tilt or obliquity. The solar system is tilted 63 degrees in relation to the galactic plane. There again, that's fortunate for us because that enables us to get a better view of the Milky Way and consequently a better view of the open clusters and nebula and things that we're looking at in our own galaxy. Okay, the solar circle is the area where the Earth and the Sun goes around the galaxy. And objects, nebula, star clusters that are located interior between us and the center of the Milky Way galaxy tend to not last very long because it's more turbulent on the interior. Clusters that are located outside of the solar circle, like one of my favorite open clusters, NGC 7789, which is in the Perseus star cluster, those tend to last longer because it's less turbulent out here. So the position of the cluster has a lot to do with its longevity within the galaxy. I found this chart or this photograph recently. Can y'all see the little lines in it? You can? This is fascinating. This is magnetism versus gravity. NASA put a telescope airplane, jet, up 45,000 feet, and it did it for 4 years, and they call it SOFIA, or Stratospheric Observatory for Infrared Astronomy. And they found all of these magnetic fields. They found that magnetic fields cause light waves emitted by dust to polarize. In other words, to line up. And once they get lined up, then gravity takes over, And this gravity versus magnetism thing, gravity always wins in the end, and all of these magnetic fields will collapse into star clusters and or stars. And this is an amazing thing because it just shows the Milky Way is just full of future stars and future star clusters. Very rarely do you see any evidence of a star before it forms. We see protostars, we see pre-main sequence stars, they're in the cocoon, but we've never seen them like this before they even get to that stage. So this is a quite remarkable photograph, and like I say, it took them 4 years to do it, but I found it to be quite amazing. All right, there are several stellar groupings, what we call stellar objects, open clusters, of course, but there's nuclear star clusters, there's superstar clusters, stellar associations, globular clusters, galaxy nucleus, stellar remnants, and asterisms. All of those qualify as star clusters. And I'll try and talk about each one of them. But first I want to mention this man, Robert Trumpler. He was a pioneer for open cluster research, star cluster research. From open clusters, he determined the Milky Way galaxy size. He came up with a diameter of only 32,000 light years, so he was a little short, but he was the first one to estimate the size of the Milky Way galaxy. And he did it using open clusters as his basis. He coined the term galactic clusters in 1925. He cataloged his own catalog of clusters, and he determined that dust caused interstellar extinction. And that puzzled astronomers for 100 years. William Herschel thought these dark nebula, what we know as dark nebula, were holes, were void spaces in the universe. Edward Emerson Bernard spent most of his life trying to figure out what these dark nebula were until he one night saw clouds in the night sky that were dark, and he realized those dark clouds were blotting out the background. So he reasoned that that's what dark nebula was, but had no idea what they were. Trumpler determined they were dust. And that was a big step forward in the knowledge of the solar system and the universe. He also has his own stellar classification, which is still used today. And Roman numeral 1 through 4 is the concentration class. The Arabic numbers 1 through 3 is the brightness classification. And PM and R is poor, medium, and rich, the number of stars. There's another, sometimes you see N, which is if he saw nebulosity in the cluster. But this man had a lot to do with the knowledge that we have today of stellar clusters and stellar evolution. All right, open clusters. This is Messier 11. It's the wild duck cluster, and it reminded someone in the past of a flock of ducks flying in formation. And I don't know if y'all can see that, but it's kind of like a V-shaped formation, and that's your ducks flying, supposedly. But it's a young cluster, 250 million years old, has 2,900 members with a mass of 5,000 solar masses. So that right there tells you this cluster is full of very large, massive stars. 2,900 members, but the mass is 5,000. So there's some big, big, heavy, massive stars in this cluster. And this star right here is the brightest star, and unfortunately, there's no Gaia data for that star, and I don't know why. Proper motion has to do with the apparent movement of stars. If that star is coming straight towards Earth or coming straight away from Earth, there is no proper motion. It's zero. In this particular case, that wasn't the case. They just did not measure the brightest star in M11 for whatever reason. but it's located inside the solar circle, which I mentioned a minute ago. All right, what is an open cluster? So I've got a few slides about this. What makes an open star clusters? They form out of the same cloud. Well, that says most of it right there. They form out of the same cloud. But if they form out of that cloud, then they've got to be relatively the same age. And it is found that younger open clusters are about 42% of open clusters are less than 100 million years old. The older clusters, there's only about 13% of open clusters that are over 1 billion years old. And there's only about 50 of those that we know of that are in the billions of years of age. This one is interesting because it's Roslin 4, which we've got on the list. It's a 10 million year old open cluster, which is very young, but is still in its birthing nebula. This is a reflection nebula. These stars formed out of that gas and dust cloud. And that gas and dust cloud is still around. Most of the time you do not see this because if the original stars were type O or type B stars, they're very massive stars, they'll blow the cloud away. And they'll retard subsequent formation of stars. But in this case, it's still hanging around and you can see it. Particularly the oval-shaped one here is fairly bright, and I can see it in my 20-inch telescope very, very easily when I observe this object. But this is, as I say, this is on the observing list. Also, since stars form out of the same cloud, they're at the same relative distance. Some on the near side are closer, some on the far side are further away, but if you're looking at something that's 30,000 light years away and there is a 500 light year difference, it doesn't really matter. It's still essentially the same distance. Stars have the same chemical composition, and it's found that only 10% of the cloud coalesces into stars before radiation pressure from these large stars completely removes the cloud or the nebula so that other stars are not able to form. This is Alessi 62, which was discovered by an amateur astronomer, and it has since become an official open cluster. So why is this particularly important? Well, if I can get this to change. In this case, since the stars are at the same distance, their apparent brightness is the real brightness. We don't run into a problem where we have a very massive bright star, but it's way in the background so we can barely see it. In this case, the brightest stars in the cluster are in fact the brightest stars, giving out the most energy. And astronomers can study that and compare that to field stars that are not in open clusters. So this is how they learned about stellar evolution. The faintest stars emit the least energy. This one, IC 4996. This is a very small cluster, but it is a beautiful cluster. And these bright members are actual members of that cluster. The age of this cluster is the youngest stars are only a little over 7 million years old. And pre-main sequence stars are still forming. Herbig-Haro objects are shooting out material within this cluster. And this is a cluster in the act of becoming an open star cluster. There are 365 stars in the cluster, and it's located 130 light years above the galaxy plane, which is unusual because being a young star, it should be on the galaxy plane, but it's not. It's above the galaxy plane. So that's kind of unusual situation. In close proximity, stars are gravitationally bound, since they're close proximity, and they have similar radial velocities and similar proper motion. And that's the two main things that we look for when we look for an open star cluster. To be stable, the internal gravity must exceed the external forces trying to rip it apart, and the stellar density needs to be above 10 stars per cubic parsec. Eventually, all stars, like our sun was once part of an open cluster. All stars become gravitationally separated from the cluster and become single stars at some point. So this is overcome at some point in the future as far as star clusters go. But here is a radial velocity plot that I made. And this shows that NGC 6910, you can see all of the stars that are moving in a southwest trajectory. Those are members of that cluster. And this is Gaia information and why Gaia is so important to what we're doing, because we can now tell with certainty these bright stars are members. That one is not. That one is going in the opposite direction. And it's going at a higher rate of speed, because the distance of each arrow indicates how fast it's moving. So this one and this one are moving at a very high rate of speed, and you can tell immediately they're not members of this open star cluster. Stars initially differ in their mass. Mass is the main difference between cluster stars within that cluster. I mentioned earlier that type O stars are more massive, and it works its way down. But your larger, more massive stars have much shorter lifetimes because they go through burning and fusing their helium and hydrogen and carbon and oxygen and nitrogen and so forth at a very fast pace. So O-type stars only have a life expectancy of about 10 million years. So if a cluster has O-type stars, which this one does, it has class B O stars, then we know that it's a 10 million year old star cluster. Type B stars have a life expectancy of about 35 million years. A-type stars are about 350 million years, and they go supernova. F-type stars are good for 3 billion years, and our sun is a G star with a life expectancy of 10 billion years. M, N stars, the small dwarf stars, have life expectancies of trillions of years. So no dwarf star has ever gone out of existence or died, and they will be around for many, many years in the future. So that is also how we know how old a cluster is. If a cluster has no O stars, no B stars, no A stars, no F stars, then we know it's got stars 10 billion years old, because the oldest stars are G stars. So that's how we know the age of these star clusters, and that's how we know this one is only 10 billion years of age. M29 has 50 members. Its distance is a little over 5,000 light years, and it is a beautiful object to look at. As I said, main difference between cluster stars is their mass. Young clusters have large differences in their mass of their stars because they have O-type stars and B-type stars and the whole bit. And as they die off, the mass distance becomes closer and closer and closer and begins to equalize as stars age, and after 1 billion years, they're roughly the same mass, very similar. All right, environment is another factor. Open clusters are found only in spiral galaxies that have gas in the spiral arms, gas and dust, and irregular galaxies, which have gas and dust throughout the galaxy, and in lenticular galaxies, which has very limited amount of gas and dust. Gas in galaxies is what gets squeezed, and that's what compresses and causes the stars to form. The dust is the glue that holds all that together. So stars need both gas and dust in order to form, and the galaxy has to have both for that to happen. Elliptical galaxies have neither. So there's no star formation in elliptical galaxies being the big spherical balls, like M87, for instance. There's no star formation in that. All right, the classic open cluster definition, it stands out from the background. That's what most people have to say when they look at an open cluster, or at least they hope it stands out from the background. Sometimes it doesn't. But in this case, we've got two objects, the NGC 457, we've got Ferraro 31. They both appear to be associated with each other, and the members appear to be together. However, and there is always a however, unfortunately, in astronomy, but are the stars related, or are they chance alignment? Is this an accident? And in point of fact, yes, it is. Those stars are not related at all. So another interesting information, thing that Gaia found out, is that 25% of the near open clusters are not open clusters at all. They're chance alignments of stars that some are closer, some are in the background, some are going this way, and some are going that way. But they're not true open clusters. And that was a big surprise to everyone. And I looked through the database of the list that Eileen and I provided and found that ESO 587-4 and Barkatova 2 are probably asterisms. Even though they're officially cataloged as open star clusters, they're probably asterisms because the proper motions are going in all different directions. So if we look here at a true open cluster, Rosalind 3, which we have on the list, the yellow members are members of the cluster, and you can see they're all going essentially in a southern direction. The anomalous or discordant members that are not part of that cluster are in red, and they're going in all different directions, all over the place. The classic example is the coat hanger, or Brocchi's cluster. You would think those stars are related if you looked at them. But we've known for years, we've said for years it was an asterism, but we didn't really know for sure. Well, thanks to Gaia, we do. Look at that. There's very rarely two stars that are going in the same direction. They're all over the place. So none of those stars in Brocchi's cluster are gravitationally related to one another. That is a true asterism. And there is a lot of them out there. All right. I read an article where someone called an asterism an incidental overdensity of stars, which I thought that was kind of a unique way of calling it. But there's a lot of ways of referring to what an asterism is. It's a chance alignment, not gravitationally bound. Milky Way clouds. I mean, you could say the Horsehead Nebula is an asterism. Divergent proper motions, many constellations, non-existent, lost, unidentified objects, or really anything your mind can dream up. And this is literally anything you can think of. When you look in your eyepiece, if you see something that looks like a figure, it could very well be unreported, and you could get it to become. If you contact the Astronomical League, they'll make it a true asterism in your name. These are some of my favorites. This is Brocchi's cluster, which is a perfect square. Dölitz 9, the pistol. These are These are true asterisms in the truest sense of the word. And this slide, this here is A for asterism. This is a friend of mine in Houston named Bram Weissman who discovered this in 2017 with a 10-inch and 12-inch telescope at our observatory site in Columbus. He was looking for a quasar, and he just stumbled across that, and he says, well, that looks like it should be something. And I think it's now a recognized object by the Astronomical League, and he told me recently that he submitted it as Mitchell's ladder, which my ladder for my 36-inch telescope is 12 feet high, and it reminded Bram of my ladder. So I don't know if he's going to do that or not. I think A for asterism is a better name. But you can see from the Gaia data, that star is going that way, that way, that way, that way. No two stars are going in the same direction. They're not gravitationally bound. This is a true asterism. And these are some other ones. There is a French amateur astronomer, Laurent Ferraro, with looks like a 13-inch telescope. He has a catalog of about 50 asterisms that he has found over the years and cataloged. This is something that anybody here can do. Just use your imagination. As I say, go out and discover some. They're there. The Kimball 2 is on the list. We call it mini Cassiopeia because it looks just like Cassiopeia. And look at that. No regularity, no gravitational attraction to any of those stars. True asterism. Stein 1, another one on our list. It looks like, if you just look at that, you'd think those stars are related. But when we put the Gaia data to it, boom, they're all going in different directions. Again, this is an asterism and not a true open cluster. Discovered in a 10-inch telescope. All right, this is an interesting object. It's Messier 73, and it's on the observing list, and it's been considered for years to be an asterism until about 20 years ago. And then they figured maybe this is a stellar remnant. A stellar remnant, by definition, is what's left over of what once was a very rich star cluster. Star clusters, over a period of time, the more dense, more massive stars move to what they call the center of the gravitational well, which is the center of the star cluster, and the stars on the periphery get lost, and over millions or billions of years, the center of the cluster is all that's left. And it looks like that may be the case here. These stars are 2 to 3 billion years old. The people that think that this is a stellar remnant did some research and came up with, initially there were 700 stars. There are now 11 stars and an extended corona around M73. I haven't been able to find that with Gaia data, but it looks like when you put the Gaia data to this, they're not going in exactly the same direction, but sort of. And if you figure that over 2 to 3 billion years that they've been doing this, they could have drifted by that much amount. Gaia, the early data release in 2020, kind of cast some doubt on that because some of the stars are 1,000 light years away, and some of the one of the stars is almost 2,300 light years away, so that's almost twice as far. So how can that be? How can they be gravitationally attracted when they're that much farther apart? But then someone wrote a paper, it's possible over 2 to 3 billion years. So it's debatable whether M73 is an asterism or what's left, or all that's left of what was once a very massive open cluster. Very massive open cluster of 700 stars. So this one they're still debating. Stellar associations. These are either the gravitational unbounding of an open cluster or open clusters that haven't had a chance to form yet. And most of the classifications are for the young clusters. The Big Dipper is a stellar association. You got 5 stars going that way and 2 stars going this way. So this is the direction of the association. It's a loose group of separating stars in general. Stellar associations have a very large diameter, roughly 700 light years, and they have over 10 to 100 plus. In some cases, they have thousands of stars. And there's 3 different types, OB associations, type O or B, very massive stars, T Tauri stars, which are stars that haven't formed yet, or R association stars that are still affiliated with their reflection nebula. But the future of this is a stream of stars, or so they believe. And these were discovered by Victor Ambartsumian of the Balyurakan Observatory in Armenia back in 1947. People made fun of him at the time. He also said galaxies expel material. People made fun of him over that too. Until in 1962, they discovered quasars throw material out of the galaxy. Victor Ambartsumian is someone I've got a lot of respect for. If he was not behind the Iron Curtain when he did all of these studies, I believe he would be regarded as highly as Albert Einstein to this day. The man was brilliant, absolutely brilliant. This is what most people think of stellar associations as being. This is in the Cygnus Rift. Its distance is 4,600 light years. And it's just, this one here, OB2, is just full of very massive stars, 2,600 type O and type B stars. That is a lot of energy coming out of that cloud right there. It's 10 times as massive as the Orion cloud, which covers most of the constellation of Orion. But unfortunately, it's hidden by the dark rift, so we don't see much of it. And then Cygnus OB9 is centered on Gamma Cygni, which is the star at the cross of Cygnus, or the Northern Cross, as some people call it. But these are stellar associations, and they're huge features. And as I said, the future for them is to end up in a stream of stars. Well, Gaia has done some work there as well. Look at that. That's streams of stars. So far, they've found 60. There's 6 merger events from dwarf galaxies in the past. One very large event around 10 billion years ago, they think. There's 170 globular clusters, which are leaving streams of stars, stellar associations, and 59 Milky Way satellites. All of these that are moving through and around the Milky Way are leaving trails of stars. And Gaia is picking up on that. So there again, this is information that a few years ago we did not have access to. All right, different types or other types of star clusters. Nuclear star clusters. These are the most massive star clusters in the universe. They have a range of anywhere from 1 million to 100 million solar masses. That's unbelievable. That is an unbelievable amount of mass. And they have diameters of up to 30, 35 light years. The Milky Way has a nuclear star cluster here, which surrounds Sagittarius A star, which is the black hole of the Milky Way galaxy, which has a mass of about 4.3 million solar masses. And it is located within 1 parsec, and if you remember, a parsec is 3.26 light years, of Sagittarius A. So this is the cluster around it. Unfortunately, we cannot see it visually because there's about 30 magnitudes of visual extinction dust between us and the center of the Milky Way. So visually we can't see it, but it can be seen with X-ray, radio bands, infrared telescopes and observations. But it had a recent starburst just a few million years ago. And of interest, the star closest to it is called S4716, and that's a member of what they call the S star cluster. These are stars right next to the black hole in the center of the Milky Way. That star is the fastest known star. It moves at 18 million miles per hour. It revolves around the entire Milky Way, around the entire black hole, in only 4 years. And remember I said it takes our sun 230 million years to go around one time. So stars moving at this rate is how we find black holes. We can't see a black hole. We can see where they are because we can determine what goes on around that black hole. And stars moving at that rate of speed have to have something very massive causing that, and that works out to be a black hole. So these are nuclear star clusters, and they're extremely dense, and most galaxies, about 75% of the galaxies that they've looked at have these, and these nuclear star clusters are what feeds that black hole and keeps it going. So they have a purpose. Superstar clusters in other galaxies are many and varied. In our galaxy, we have two of them. One here is the Arches star cluster. It's named because it is in the constellation Sagittarius, the Archer. It's located 85 light years from the center, and it's the densest packed star cluster in the Milky Way. If the sun area were as populated, there would be 100,000 stars between us and Proxima Centauri, the closest star to the Earth. That's only 4 light years away. Can you imagine 100,000 stars in a distance of 4 light years? That's incredible. That's what we're looking at here. They call these superstar clusters, and they're quite prevalent in other galaxies, as you will see. This one has over 100,000 stars, and some of them are up to 130 solar masses. It's figured that in our present epoch, the most massive star that can form is about 150 solar masses, or 150 times as massive as our sun. So this is full of very large, massive stars. And again, you can't see it because of the dust extinction. The other superstar cluster is a quintuplet star cluster. Its age is only 4 million years of age, and it has the brightest star in the galaxy called the Pistol star, and it's 100 light years from the galactic center. It's named the quintuplet cluster because it has 5 prominent infrared sources, and again, we can't see it because of the extinction of 30 visual magnitudes. Omega Centauri. I'm told you guys can barely see it from up here. I put a plea in to get you guys to come to the Texas Star Party. You can see it very well from down there. And I've talked to some people that have come to TSP just to see this object. It's spectacular. Absolutely spectacular. It is officially listed as a globular cluster. It is the largest globular cluster or the most massive globular cluster in the Milky Way. It has 4 million solar masses of material squeezed into this small area. However, Gaia has found out this is not a globular cluster at all. It's a galaxy nucleus. It's what was once the core of probably a dwarf galaxy. that interacted with the Milky Way galaxy on a highly inclined orbit, and that is why it is so massive. As I say, it's the most massive cluster in the Milky Way. There's only one cluster that's bigger, and that goes by the name of G1 or Mayall 2, and that is in the Andromeda galaxy. And it is even larger than this, and it is a similar feature, a core of another galaxy and not a true globular cluster. So that's another big discovery that Gaia has made. 10 million stars, 17,000 light years. It's only 10 light years across, and it's got 10 million stars packed into that small area. That's quite phenomenal. And it is beautiful to see in a telescope, in any size telescope. All right, the difference in open clusters and globular clusters. Most of these are obvious. Open clusters are loosely structured, tightly structured. Few stars, millions of stars, a single generation of stars, multiple generation of stars. And this is the big difference that they're finding now in the two. A single generation of stars, open clusters don't have time to manufacture a second generation of stars. Whereas globular clusters, because they're dense, there's a lot of stars there, and there's a lot of gravity, and it keeps the material in. So when the stars go boom, supernova, that material doesn't go very far, and subsequent stars can form out of what was expelled by those stars in something of the gravitational attraction of a globular cluster. And there's something called the sodium-oxygen anticorrelation that they're finding only applies to large, massive objects. It has an unduly high amount of sodium to oxygen. You do not see that in field stars. You do not see that in open clusters. So that's one difference between globular clusters and open clusters, and currently probably the main difference that astronomers go by. Open clusters continue to form stars. Globular clusters are no longer forming stars. These are in the spiral arms near the plane, as I mentioned. These orbit around and through the galaxy. These have young stars of variable mass. These have very old stars of similar mass. And these are irregularly shaped, where these are highly symmetrical. But then, as I said earlier, there is another however. There are objects like Berkeley 46 or NGC 6791. They don't know what to categorize this as, and I'll talk about that in a few minutes. There are a few exceptions that can go either way: globular cluster, open cluster, or core of another galaxy even. All right, stellar clusters and star-forming regions in other galaxies which are visible in amateur telescopes. This is what I do at the Texas Star Party with the advanced program. Get people to look at things in other galaxies. And it's quite easy if you know what to look for and where to look. I'm going to go through this kind of quickly, if I can get this to change. There. All right, NGC 4038 and 4039. That should be 39. The antenna. These are two highly interacting galaxies. The nearest major merger of two large galaxies, their distance is 45 million light years away, which is in the Virgo galaxy cluster. But yet, all of this detail you can see in small to medium-sized amateur telescopes. In my 20 and 36-inch telescope, those are iridescent. They're just obvious. They stand out. And these are two galaxies, NGC 4038, which was a very gas-rich spiral galaxy. NGC 4039 was a gas-poor spiral galaxy. And 9 million years ago, they began to approach. 600 million years ago, they passed completely through each other. And in doing so, all the glass, or most of the gas, was removed from 4039, which was gas poor to begin with. So that's just why you see most of the activity up here, because 4038 retained most of the gas from that interaction. 300 million years ago, the tails, the tails were released. And in 15 million years and 5 million years ago, you had the interactions which caused all of this. The 5 million year old incident is the most recent and what we're seeing now. In about 400 million years from now, this will be one galaxy. But these are H2 regions. These glowing regions are H2 regions. And they're very young, 5 to 10 million, 600 million years, 15 billion years in the case of the cores of these two galaxies. And most of the gas and dust is in this center here. This is the overlap. This is the overlap region for the two galaxies. And it's very young, at only 5 million years. So if we look at the open clusters within the antenna, we've got these OC1, OC2, and so on and so forth. All of these clusters are very young. In all, there's 14,000 point-like objects that have been found in these two galaxies. 8,000 of them are young clusters. And many of these are young globular clusters that are being formed by the compression of the gas and dust in these two galaxies as they come together. But the ages of the open clusters are 8.1, 6.6, 10. These are all very young, but look at the mass. The mass of these clusters, 2 million solar masses, 3 million solar masses, 3 million solar masses. I mentioned earlier the Arches star cluster, the densest cluster in our Milky Way is 70,000 solar masses. The mass of our nuclear star cluster is only 1 million. These jobs are 2 and 3 million solar masses. These are gigantic star formation events. And that is also why we're able to see them as well as we are across 45 million light years. And by the way, the published data on these open clusters, it says they're 18 and 19th magnitude. Don't let that scare you. I've seen them in my 20-inch telescope. They're little points of light that pop out. They're not that faint. So when you see something like that, it's kind of neat if you're a visual observer. Not only do you see the H2 regions, which these stars are illuminating, but you see the stars themselves in another galaxy. Me, I get off on that kind of stuff. That's why I'm a visual astronomer. Can we move that some way? All right, NGC 4214. This is another very active galaxy that you can see the H2 regions inside, here, and here. And here again, these are very massive complexes. The largest is 3.5 million years old. The youngest region is down here. This is the highest H2 energy events. The nucleus of the galaxy is this, and this here is an old superstar cluster. This is multiple star clusters. All of these you can see in a telescope. Again, you're looking across, in this case, you're only looking across 10 million light years, which is close, but nevertheless, it's detail inside another galaxy that is visible. And that to me is exciting. But all of these clusters are young. 4 million years, 3 million years, 3.5 million years. And most of these H2 regions are illuminated by superstar clusters, like the Arches cluster in our Milky Way galaxy, for instance. What happened? All right, NGC 4449. This is a starburst galaxy. And to be a starburst galaxy, the star formation rate needs to exceed the average by a factor of at least 2 or 3. This is a dwarf galaxy, and most dwarf galaxies are not areas where you get star formation, but it's popping off in this one big time. This might be the easiest one to see this detail because it's all over the place. Star formation has been continuous. The first few years it was slow. The last 500 to 100 million years ago, multiple events. And then recently, less than 10 million years ago, the star formation rate has been 1.5 solar masses per year. This is occurring inside of these H2 regions. Within this cluster, 60 to 75% of the stellar population is above 1 billion years. 20 to 25% of the clusters are less than 100 million years old. So most of the clusters are older than the younger clusters, which is a little bit unusual. There's 61 star clusters that they know of, and so far they've found 14 globular clusters that are 9 billion years of age. And when you look at it, you see this is easy. This and this is easy. This is a star. So you can use this star kind of as a key to go around everywhere else. And if you spend a good half hour looking at this thing, you'll be amazed at what you can see within NGC 4449. And M82, everyone's favorite that they look at, these are individual H2 regions. These are star-forming regions. Region A here is 500 million years of age and has had subsequent eruptions. There's 86 superstar clusters inside of that cloud. And it is rotating rapidly, and it's inclined 22 degrees to the rotation of the galaxy, interestingly enough. Area B has 113 young clusters. C is rotating, but it's rotating opposite A. And one of my favorites is H right here. That is a single compact superstar cluster, or it may be a young globular cluster. But you can see that. It's 15th magnitude. It's right on the dust lane. You can see it here. And it has been reported numerous times as being a supernova in M82. When point of fact, it is a star cluster in another galaxy that's 11.42 million light years away. So these are clusters that you can see in other galaxies easily. This is M101 again, and I've just highlighted this one, and this one. But all of those are NGC objects. There's 10 NGC objects within Messier 101. These NGC objects are H2 regions and superstar clusters that can be seen and photographed in amateur telescopes. There are also many X-ray binary stars, which are two stars that are feeding off. One is feeding off the other star and creating X-rays, and that's creating a lot of energy, and which is how we see these as well as we do. Of interest is this one right here, 5471. When you look at it in a telescope, that looks very blue, almost iridescent blue, and it's very round. And it's classified as an H2 region of the galaxy, but they don't know what it is. Some people think it's another galaxy. Gaia has its distance at 16 million light years, whereas the galaxy proper is 20 million light years. So it could be a foreground galaxy, or it could be possibly an H2 region. There are 33 H2 regions inside of it, 5 knots inside of it, but it's very bright, and it does not look like any of the rest of these when you look at it visually through a telescope. So that's an interesting feature. All right, back to our Milky Way galaxy. The sun is here. We are a barred spiral galaxy. That bar is about 16,000 light years in length. The diameter of our Milky Way galaxy is 180,000 light years. We're rotating at 565,000 miles per hour. There's 400 billion stars in the Milky Way, and Gaia has found that we now have 4 spiral arms, 4 gas and young arms, and we're orbiting about 230 million years to complete one orbit. By the end of my talk, and it looks like the way it's going it will be, we will have traveled 850,000 miles. Doesn't feel like it, but we've moved quite a distance. As far as open clusters and what we can see, out of an estimated 100,000 open clusters, we've only cataloged 4,000. The problem is the dust and the bar. We can't see the other side of the galaxy. When it comes to open clusters, we can see only 5% of the way through the galaxy. Open clusters, we can only see what's around us. There's the arches in the quintuplet star cluster there. But the other side is blank. Embedded clusters are stars that are forming, T-Tauri stars, pre-main sequence stars. They're still in their birthing cocoons. We can do a little better job there because they're radiating in the infrared, and infrared telescopes can penetrate through dust better than visual light does. So we can see a little bit more, but still, that's not very good. So there's a lot of work to be done as far as open clusters. Stellar clusters discovered by amateurs. Alessi clusters were discovered by Bruno Alessi. He's a Brazilian amateur astronomer at the University of Sao Paulo. And there are 41 categorized Alessi objects. And these were discovered using the Tycho 2 catalog, just looking in a catalog. But these are some clusters. This is one that's on the list. Here's one of my MAC galaxies here, which is unusual because usually you don't see galaxies with open clusters. But nevertheless, there's one right there. That's what it looks like, and it's a very nice-looking spiral galaxy. 390 million light years away, so it's definitely in the background. Matthias Kronberger is another amateur astronomer out of Innsbruck, Austria, and he listed 82 Kronberger objects. Only 41 are considered open clusters, but he reported them in 2006 by examining the Digital Sky Survey and the 2-micron all-sky survey charts, just looking at photographs, and made himself famous as far as open clusters. These are pretty faint, but nevertheless, there's a nice one right there, Kronberger 54. I've seen that several times, and it's not a bad open cluster. A lot of these I didn't have on the list because they're up in the summertime and they're not available to be seen here at Stellafane. Philip Tuch, another Austrian astronomer, listed 173 objects. Only 146 were considered open clusters, and he also examined DSS and SS2 charts. But these are some open clusters that Mr. Tuch discovered. He also identified 50 planetary nebulae. Not looking through telescopes, just looking at photographs. So I mentioned earlier, 4,000 open clusters out of a potential 100,000. There's a big area for people to make discoveries. Most of the recent discoveries have unfortunately been in the infrared, which we can't see visually. But nevertheless, they're out there and people are discovering them. NGC 7789 is on the list. This may be the most beautiful open cluster, to me anyway. It was discovered by William Herschel's sister, Caroline, which is why it's called Caroline's Rose. And it's in the constellation of Cassiopeia. It's a fairly old cluster, up to about 1.6 billion years of age. It has 700 members, 7,000 light years away, but its claim to fame is it is full of a certain type of star called a blue straggler. In this case, there's 30 blue stragglers that have been identified by Gaia, and I've identified just a few of the brighter ones. And these are easily seen in any telescope. They're not blue because they appear blue, although they do, but they're on the blue part of the Hertzsprung-Russell diagram over here. This is an HR diagram. This is the blue side. This is the red side. And blue stragglers are stars that should not exist. They were discovered in 1953 by Alan Sandage. And as I mentioned earlier, the more massive stars die out, and then the less massive stars, and the less massive stars. The oldest stars in the cluster are right here at the turnout. The O, B, A stars have gone supernova and no longer exist. So the oldest stars in the cluster should be right here at what we call the main sequence turnoff. But yet, there are stars above it. Those stars should not be there, and those stars are blue stragglers. And they don't know for sure what they are, but the current thinking is it's two stars that came together and formed one. They're either a collision of two stars or what they call the vampire model, where two binary stars merge into one. Two old stars merge into one, and as such, they mimic a younger star by becoming combined into the one star. And that's what we're seeing here. And there's another group of stars called blue lurkers, which these are very similar, but they're lower mass stars, and they're in the main sequence. And the main way that they determine these are the rotation of the stars. Older stars slow down their rotation rate as they get older, and that is measurable. Our sun is 4.5 billion years old, and it rotates once in about 30 days or so. If these were a G2 star like our sun, and they've measured some, they rotate in 12 to 15 hours, or 12 to 15 days. So they rotate much faster, and the thinking is, if you see the Olympics, the skaters, when they're spinning, and their arms are out and they're turning, but as they pull their arms in, they go faster and faster and faster and faster. You take two stars, they're taking up this much space, and you move them into one star taking up this much space. It's the same thing. They spin up. And that's how they know these are blue. Well, that's how they know these blue lurkers in here with these other stars, which are rotating at a very slower pace, that these are also stars like the blue stragglers. This is theoretical, but they're pretty sure that is what is going on here. That these blue stragglers, they're finding them everywhere in older star clusters, like M89. Berkeley 46. Well, I need to rush. I could make a whole talk on this thing. This is the most unusual cluster one of the most unusual objects in the entire sky. It has an age of 8.5 to 10 billion years. It's the oldest open cluster we know of, yet it has a metallicity of 0.4, iron to hydrogen ratio of 0.4. It's the most metal-rich open cluster that we know of. It's twice the metallicity of our sun. The original stars were hydrogen and helium only, and as those stars went supernova, they created heavier elements, and then heavier elements were created from that adjustment. And consequently, we end up with what we have today, the calcium and the carbon in our bodies, the metal in this building, the Earth. Those are metals formed over billions of years from stars that existed previously. Well, how do we have something that formed only 5 billion years after the Big Bang event, and it has twice the metal content of what we have today in our sun, which formed, it took 9 billion years for it to form. So that has thrown people for years. There's been many a paper written about that. And the answer is the mass. There are so many stars here that when stars went supernova, the metals that they created did not escape the constellation or the cluster. It stayed in, so subsequent stars formed out of enriched metal gas. And then those formed out of even more rich metal gas. So it's the gravitational attraction of all of these stars which is the answer to that enigma. And it took astronomers probably 50 years to figure that out. And it's interesting in other ways. It has 128,000 members, but a mass of only 5,000. So that tells us these are very small stars. There's very little mass compared to how many stars there are. So even though this is 8 billion years in the making, it will be around for many billions of years more, because those small stars aren't going anywhere. This is a HR diagram of it. This is a Gaia plot. It shows all of the red lines, the red arrows. These are crew members, cluster members. And there's 3 generations of stars here. It also has a sodium-oxygen anticorrelation, which I won't go into again. The white dwarf luminosity function. White dwarfs have no energy source. And so these are undermassive stars that never went through what we call the helium flash. So the cores of these stars are made out of helium, and those last 3 times longer than the carbon-oxygen core of most dwarf stars. So consequently, we've got 6 billion-year-old stars, 4 billion-year-old stars, and 8 billion-year-old stars. You don't see that anywhere else. So that's another reason why I read a report where a guy said there is nothing else that's even remotely like NGC 6791. This is in a category by itself. All right, NGC 188, this is similar. It's 4.5 to 7 billion years old. It has a distance of 15,800 light years away. About 50% of these stars are multiple systems. Someone figured that 40% of the stars in our Milky Way galaxy are binary or multiple star systems. It also has a good collection of blue stragglers, 24 to be exact. And it is very large. It is larger than this picture here. It's as large as 2 times the moon's diameter. It takes up a full degree of the night sky. So it's a very large but very massive and very old open cluster, NGC 188. It's very near Polaris, the North Star. NGC 6520 down in Sagittarius. Unfortunately, we didn't have the sky the other night to look at this, but it's a beautiful object. Looks like a flower with the center of the flower. And right next to it is Bernard 86, one of the dark nebula that drove E.E. Bernard crazy trying to figure out what it was. But of interest, these 2 objects are at the same distance, about 6,500 light years away, but it's just a chance alignment of 2 ships passing in the night because they did not come from the same place. They have different radial velocities. The cluster has a radial velocity of minus 23, Bernard 86 of minus 11. So they came from different places. They just happen to be at the same place now for us to observe. And both of them make a very nice visual image in any telescope. But of interest is the central star. It's the brightest star. Is it an actual member or not? It has a V magnitude of 8.1, and it looks like it's a foreground object. It looks to not be part of the cluster, but when we put the Gaia information on it, kaboom! It has the same proper motion as the rest of the stars. So it is just a much more massive star than the rest of the stars in the cluster. It is probably a type O or type B star, which means that tells us right there this is a very young star cluster. It has to be, or that star would not exist. It would have gone supernova 10 million years ago or so. So this is a little more. This is some more information of what we can glean from the Gaia spacecraft. NGC 457, the Owl cluster. This is similar. It's a very young cluster at 21 million years, 60 stars. Of interest are these two bright stars. Are those stars related to the rest of the cluster? Phi 1 Cassiopeia, this one here, is one of the brightest stars that we know of. It's much brighter than one of the brightest stars in our Milky Way, the Rigel in the Orion constellation. It's much brighter than that, much more luminous. But is it a cluster member? Well, Gaia answered that, yes. It's got the same proper motion as the rest of the stars. There's a few that are not. I mean, here's one going in the wrong direction at a higher rate of speed. But you can see that this is a true open cluster. And both of these brighter stars are in fact actual members of that cluster and not foreground objects, which is what they appear to be. So, I have a book coming out. It's supposed to be published in September. That may or may not happen, but that's the date, by the American Astronomical Society. And on the cover, I've got one of my favorite friends, NGC 4449, which I talked about earlier, with all of the visual activity going on inside the cluster. One of my astronomical heroes, Leslie Peltier, the great amateur astronomer, he once suggested a cure for many of the world's problems is simply one gentle dose of starlight to be taken each night just before retiring. I think all of us would agree with that. I certainly would. So this is a listing, a view of all of the stars on this year's list, observing list. This is the pin that Eileen made out. This is me and my new telescope, my new 30-inch telescope, which I dearly love looking through. And with that, I thank you. I thank the stars. And I got 3 minutes. Do we have time for questions or? Oh, yes.
You mentioned getting one galaxy going through another when they merge. Is it kind of like an oscillation sets up where they kind of like go, gain momentum, then through and then like that?
Well, actually, they go through, and the theory is that there's so much space between stars that no two stars will ever collide. But they'll go actually through each other and around. But that orbit will get narrower, and it will get narrower. And I believe that was NGC 40, 38, and 49. The last passage was like 4 million years ago, and that's what we're seeing now. So yeah, they go through, they orbit around, they may go through again, but it gets smaller and smaller and smaller, and eventually they become one galaxy. Yes?
I did the binocular and telescope Olympics on Thursday night, and Stein won. That was a neat little grouping.
Stein won?
Yeah.
It is, yeah. Those asterisms, when you see them, they don't look real almost. I mean, it almost looks like somebody planted something up there because they just couldn't possibly be like that brooches that rectangular cluster that I saw that I showed y'all. It doesn't look like a real object, but it is. But yeah, I mean, some of these things are absolutely gorgeous. Yes. Yeah. Is there a distinction between a stellar association and a moving group, or are they the same? But the same. The question is the Ursa Major or the Big Dipper is called a moving group. Is it the same as a stellar association? And the answer to that is yes, it is. Yeah, they are. It's a loose. They're somewhat gravitationally bound, but only somewhat, and they won't last. I mean, anything that comes by will pull it out of the group. So it's very loosely held together. But yeah, they're the same thing. Okay, all right. I thank you guys.